Thank you so much, and thank you so much for having me. I also want to particularly thank Anna because she gave me all the introduction already. And so I actually, this whole topic is something that we do long enough that there are kind of various application kind of collecting. And I decided this time to brutally just show just the first introduction and then show just one of the applications. And I'm very happy to talk about more in the break or something like that. I also would like to mention that we have yet a completely different kind of formalism to solve this all, which is very different from both what Anna is doing and also what Ash is doing. And I would love to discuss this too in case anybody is interested. Okay, so what I am going to talk about is cooperative 2D arrays. And with cooperative, I mean exactly what Anna has defined today in the morning. And I think you have also mentioned that you will talk about the mirrors, so you might not have to do that anymore because I will introduce it. That's what I thought. Okay, so we imagine an array of radiators in 2D ordered. And these radiators, they could be excitons, they could be nanoparticles or so. So for most, it's the easiest to imagine them just as two-level atoms. And that's also how I will describe them through most of the talk. The nice thing about such an array is that it can have a very strong optical response, which can be very well engineered. And so our first idea was to call this atomic matter surfaces, because you really do the engineering similar to what you do with metamaterials. So the start for us in this field was this idea with the mirror or reflectivity. And this is basically, for me, the starting point of a lot of application, and in particular this QED and metrology application that I will be talking about today. So in particular, we have this array. And it's important to remember that this has a lattice constant, which is of the order but somewhat smaller than the resonant wavelengths. That's usually when this cooperativity, this dipole-dipole interaction, etc., really kicks in. This is a smooth transition. It's not like that if you are at 1.1 lambda, there's no cooperativity, and if you are at 0.9 lambda, it's super cooperative, it's smooth. But there is a somewhat sharp transition. And that's the diffraction order. That is really sharp for exactly A equals to lambda. And at A equals to lambda, it also there is a singularity in the system, which you will see in a second. So in our case, A is smaller than lambda. And why is this interesting from a point of view of these atoms? And why did I put these circles around my atoms here? So what is the size of a single atom for a quantum optician? When we do first kind of quantum 1 or something like that, we learn, oh yeah, there's the Bohr radius, it's somewhere a fraction of an angstrom, right? For quantum optics, the size of an atom is the cross-section of an atom with resonant light. And that's of the order of the wavelengths of the resonance, or actually of the order of the wavelength squared. So that means if we have a lattice constant that is of the order or smaller than the wavelengths, that basically at that point, the sizes of the atoms pretty much tile the whole plane. So you can see the fact that even though we have a somewhat dilute sample of atoms here, you can see that really as a kind of a wall for light. And this is why the kind of intuitive feeling why things become different. That was actually also the way how this started for us. Namely, Markus Greiner and we met on the corridor at some point, and he said, oh, we are planning this erbium accordion experiment where they exactly get in this regime. This experiment, by the way, is the one that's running now and that Anna has kind of mentioned in the morning today. and I don't know exactly what to expect. So my first thought was, if I send some light in here, that this should somehow reflect stronger in this regime than if we go a little bit further away by some kind of nonlinear kind of factor. But I don't quite understand it. We can't calculate it. Do you think you can have a look at this? I said, no problem. My postdoc, Effie Chamon, by that time, who is now professor at Weizmann, sat down, did this calculation. Honestly, he did it in an afternoon. It's once you know how to do it, it's a very simple calculation. And what he found was actually very surprising. Namely, one does get actually complete reflection if you send in a photon in the normal direction, in this case, but only for two particular cases. Namely, if A over lambda is either 0.2 or 0.8. This was, to start with, numerical results and was very surprising. There was absolutely nothing kind of intuitive about this. So we thought, this is really cool. Let's dig a little bit deeper into this. This is out of the paper. It's a little bit prettier version of what I showed you before. And then what do you do first? In a case like this, you go on the archive and see whether somebody else has found this already. So we went on the archive. We found a really nice paper, which kind of was on the archive since about 10 days. So, and they exactly found the same thing. They missed this lower resonance, and I can tell you why, but I'm not. So we thought, okay, well, I guess we need to buckle down and work a little bit harder and not just tell that we found this interesting phenomenon, but we have to find an explanation for it. And so in the next 2 or 3 slides, I explain this to you.
The incidence is normal or it's a manual?
It actually, we did the calculation for normal, but it turns out it's very, very robust. So you can come nearly totally flat, and you still get this. So that's actually a very good question. So it's not Bragg. It's nearly not at all angle dependent. So what I would like to remind you at this point is that this is really, as I say, it's not Bragg. It's not that these reflections from the different atoms interfere. It is really cooperativity. There's some very serious nonlinearity there. So let's step back a little bit. Let's do the very simplest math for this case that we can imagine and look at the field, and what I said, we assumed the simplest case. We assume an infinitely large lattice with just plain wave with normal incidence. That simplest case that you can imagine. In this case, the incoming wave is E0 times e to the ikzz. And then we calculate what the outgoing wave is. That's obviously incoming wave plus the scattering, which goes in both directions with some kind of scattering constant, S. And so what we therefore need to calculate is what is S. And if you stare at this just slightly closer, you will see that if S happens to be -1, the forward direction is cancels out and we get everything back. That would be the place of our total reflection. So we just have to calculate S. How do we do that? So this is what we need. So we do exactly this kind of Green's function calculation, etc., that Anna described to you today in the morning in some detail, which comes out to a complex number for which we call the real part delta collective and the imaginary part gamma collective over 2. And then we calculate first the polarizability, and from the polarizability, the scattering constant. And this is the form that we get. And if you look at that, you see that this is in principle just the Lorentzian, right? We have a decay, a detuning, and a decay again. And this one is actually happens to be the same if you look at Derek's old papers, for example, that you get if you couple a single atom to a 1D waveguide. In that case, you don't get anything collective, but the form is the same. In this case, you also get total reflection back. And here we get this. So if you look at this and you say, okay, this delta is just the tuning between the incoming light and the resonance. If the sum of these two is 0, then S is exactly equal to -1. Very easy to see, right? So this means that the only thing that we have to now to find is when is this delta outside plus delta collective equal to 0? The delta outside we can choose. The delta collective is a function of all the system parameters, and that one can actually only be done numerically. So, but it's a very simple, it's just basically an infinite sum that we have to solve for this, which comes out of this interaction between all of the possible atom pairs here. Okay, so we do this. Sorry, I'm always a little bit behind with my showing. So this is the form. I have to apologize. I have to change this picture at some point because blue here is down and red is up. So it's the wrong way around. But this is the form that we get for delta collective. And as we can see, this has singularities both at 0. Well, that's not very surprising because if we do put two particles that dipole-dipole interact infinitely close, then we get a singularity from the interaction here. And similarly, we get a singularity at A equal to lambda. But in between, this is just some kind of analytic function with maximum in this direction, minimum in the other direction. And if we now look let's assume we are completely on resonance, then we just look, when is this delta collective equal to 0? Well, at 0.8 and at 0.2. The reason that we get exactly these numbers is just kind of the consequence that the square lattice has pretty high symmetry and comes out to such nice numbers. We can do that also for other lattices, in which case we also get two numbers which are somewhat similar, but they are not so nice and even. But it was lucky that we started with the square lattice, because if it would be two other numbers that are somehow odd, we probably never would have followed this up. We were just intrigued by the 0.2 and 0.8. Then we can plot for this actually the reflection coefficient. This is this blue curve here, and we see that this is actually not true. It's the yellow curve, I'm sorry. This yellow curve, which we see, is maximum exactly at these two cases. And then, of course, we can change the detuning a little bit and get other curves. And obviously, there can be something like too much detuning, right, for which you don't get it anymore. But in principle, you can now get this reflectivity if you choose the right detuning anywhere for any A between 0 and 1 lambda. Okay, and as I said, this doesn't have to be a square lattice, can be any other lattice. So this is the first property of these kind of lattices, that we have this reflectivity, which is really very, very simple. And as I said, we did this numerically for Gaussian waves and for finite lattices and for different incident angles, and looking how the ordinary and the extraordinary waves kind of scatter into each other, all of that kind of stuff. It's a super clean system. We get still in the 99 point something %, even if we take the oddest angle and direction and so on. So this is the one thing. The other thing is, let's look at the band structure of this. So for this, I would just very briefly introduce what the light cone is, because I figure otherwise I spend always in extraordinary amounts explaining that without a slide. So the light cone means that's the parameter volume where on the plane the kx squared plus ky squared square root is smaller than the k value that we get in vacuum. Okay, so that's what we would see as normal. But due to the fact that we have this material interaction, this also can be bigger than this one. Okay, obviously, if that is the case, there is no coupling anymore between the two. So this is why we call it light cone, because there is really a qualitative difference between inside and outside. So yeah, exactly. So if we look at the Brillouin zone for a lattice constant that is smaller than the wavelengths, the light cone is actually smaller than the Brillouin zone. So in that case, it actually plays a role. So this is another of this, why this A smaller than lambda versus larger than lambda actually matters. So this is basically how the Brillouin zone looks like for a square lattice. And we have, in this case, when A is smaller than lambda, the light cone that looks something like that. So everything which is somehow around this symmetry point, we have this normal situation where kx squared plus ky squared is smaller than the k vacuum. So that means that there is always a way how to couple to the vacuum. If we take kx squared plus ky squared plus kz squared, but if kx squared plus ky squared is already larger than k vacuum, there's no way to couple to the vacuum. So that's why we get this particular kind of band structure where we see that inside the light cone, the band structure is very different from outside, a different color, just different polarizations. And in particular, so here we have this in light cone, so in which excitation on the lattice coupled to the far field or to the and so we get emission from the surface, but if we are outside of the light cone, that doesn't happen anymore. So that means if we get some excitation somewhere in this area of the Brillouin zone outside the light cone, we have a perfect waveguide, just with this kind of array here, because it cannot couple to the waveguide anymore. Of course, it's also hard to couple the excitations in, right? It's not only hard to couple them out, it's also hard to couple them in. And how to actually couple them in, we have already in our first paper a couple of examples, but one of the ones how one can do that are impurities, and that's what a good part of my talk is today. How can one implement that? Well, atoms in optical lattice is the obvious, and this is also this kind of Bloch paper that was already cited before today. One can also imagine 2D semiconductors like transition metal dichiral cargenides. And as it turns out, Hong Kun and Philip at Harvard had actually seen a similar reflection pretty much within a few months of our paper here. But I will let's assume atoms for now. Okay, so next step. Let's think about this cross-section again, which is lambda squared, and think about if we set this atom as an impurity in such an array, whether we can actually make the cross-section effectively as big as the array. That's the next goal, okay? So, in this case, I just show you how the scattering intensity looks like. If we have only an impurity, that means just only a single lonely atom. In this case, you get a near field scattering, which is a little bit higher, but you get a far field scattering, which we gauge to 1. Or we can also look at the array alone, in which case we get the full reflection. Here we tune a little bit away, so if you look closely, you see there's still a little bit of light going through. Obviously, there's a standing wave, and because of interference, with the same scaling that we have here, the intensity here goes to 4. But if we put them together, it actually gets really high. Okay, so that suggests that if we send a light in on the array that has this impurity, and the impurity, of course, has to be chosen correctly, basically all the scattering immediately kind of collects on this impurity. So let's look into this, and I'm not, this is mostly numerical, but I will try to give a little bit of an intuition why this is the case. So classically, people use antenna arrays in order to kind of collect radiation, classical radiation, a little bit more efficient. We can do in principle the same thing with quantum, but here we also use the idea of virtual excitation of the array atoms. That's not the case that we get in these antenna arrays. And we get the virtual excitation basically by exciting slightly outside the resonance window of the array atoms. And in that case, we send our light in there, and it basically immediately collects all on the impurity. How can one potentially measure this? It's not quite measuring in the sense of what we heard from Amir, but I'm trying to get in this direction. So one way is to say, okay, let's assume we have 2 impurities on the array, and we excite one of them, and we see how does it wander to the other one. It has to somehow couple to the array. So now you might already kind of guess why I called my talk something with QED. Because this array is now a mediator for the excitation on these two impurities, which is very similar to if we put these 2 impurities or 2 atoms in a cavity. So here we are looking just how does that coherently exchange population, and we try to kind of quantify that when we by saying, okay, let's measure the coupling or simulate the coupling versus the decay, and let's call that quality factor. And what we get in this case is something that looks a little bit like Rabi oscillation. It is not. It is the oscillation of the excitation. So that's impurity 1, impurity 2, and here I just plot the population on these impurities. This is in a certain parameter region, but I can choose a better parameter region in which we get actually very, very good oscillations with a very high quality factor. And here these parameter plots here have A over lambda on the x-axis and the detuning on the y-axis. And as we can see, we can get quality factors of up to the 10 to the 6 or so if we choose our parameters the right way. So with that, we can do a couple of nice things. We can, for example, think about doing an on-array quantum computer. In this case, we need an extra control. Namely, we need to go, for example, in a 3-level system and use so-called electromagnetically induced transparency, which I'm not going to explain now, in order to couple or decouple the impurities from talking to the array. But if we can do this, we can basically have each of these impurity be a qubit, and we can let them talk to each other, in principle, build then gates, etc. So this is probably not the best quantum computer ever invented, but it kind of shows you what this in principle can do, and we have calculated what the fidelities would be, etc. It looks pretty good. So, but with the last kind of, I think, 3 or 4 minutes that I have left, I want to look at this quality factor again. So here is the same picture again that I showed you before. But what I have in orange and blue here is actually the two black curves here. This new orange and blue curve that I have are the populations if these 2 impurities don't have exactly the same transition frequency. In this case, this population exchange is not complete anymore. And it turns out it is not just sensitive, it's very sensitive to a detuning. And this one kind of calls automatically for a potential application in metrology. And so what I will show now is I call my 2 impurities the excitation and the detection impurity. And I start with this particular picture. Hello? And here, just a brief note on this is the only slide I have with some equations. So non-Hermitian Hamiltonian, fortunately, all my pre-speakers today have talked about that already, so I don't need to talk about that. But what comes out of that is that we get a nonlinear frequency dependence, which is actually near an exceptional point, but it is not a typical exceptional point nonlinearity, because those are actually very, very unstable. What we have is very stable. But it turns out that the parameter regions where you get exceptional points and what works for us are very similar. So I just show you the end. Yeah.
Can you clarify stable or unstable in what sense exactly?
Against noise. So, yeah, robust, yes. I should have said that. Thank you so much. Yep. So I just show you how the amplitude of this looks like, just to show you the type of nonlinearity. This is all analytically done, but I'm not doing but there is kappa is this coupling between the two, between the impurities and then the array, and S is this exceptional point branch amplitude, and as you can see, this is very nonlinear. We can also calculate the variance, and here is basically the same picture again, but we only look at the detection. And we see that this, if we are not perfect, of course, eventually this oscillations go down, but the oscillation with the tuning look very different from the oscillation without the tuning. And not only do they become much smaller, they also become much faster. That could also be something that can be detected. Here is the detuning, is this population, maximal population exchange as a function of the detuning from each other. And here, this one I will leave out. And here is basically our figure of merit, where we look how much can we actually line narrow this. This is kind of, this looks like an absolute figure. It's not, because it depends on so many parameters that there's no way to ever completely, but this is kind of normal. Ignore these two curves, but this orange curve here basically gives the line narrowing fraction as a function of the lattice spacing. And what you see is that we get basically a kind of a full to zero kind of decay in population transfer of for a frequency that is 10 to the 5 times the line width of the impurity. And with that, I should tell you that it already makes sense to kind of choose this impurity with a relatively narrow line width, because that's what you would do for metrology. And at the end, and of course now I really need to kind of jump over a couple of slides here. One very last thing I would like to do, because I mentioned the robustness. So the point is, normally, this works very nice. We get really super high, we get 10 to the minus 5, etc. And we could imagine, for example, to say, okay, we want to detect the gravitational redshift between this position and this position. Okay? Can be done in principle. We just need to choose the line widths of these impurities a priori narrow enough. But of course, the point is, experimentally, this is not how this looks like. Because, hello? What we get, now it doesn't work anymore. Okay, I know why. Because what we get, I mean, our impurities might not sit exactly in the middle, in which case our signal vanishes. Or the array atoms, they might be a little bit kind of disturbed, in which way our signal gets lost. But what we can do is we can actually re-gauge the system and just say, okay, let's isolate the system. Let's make sure that they look like they're on resonance again. And then let's do the measurement again. And it actually turns out that you can nearly get back to the original form, which we actually see here. So here we get not quite to 10 to the minus 5, but nearly. Just by re-gauging the system, even with disorder up to 10% of the position. And here's also the standard deviation. I will leave that out, and I just want to finish by at least showing my collaborators. Now I can't do that anymore. Well, I thank you, and if you have questions, I pull up my collaborators in the meantime. Thank you so much.